All right, let's solve this benzene and toluene mixing problem. So hopefully you have this set up from last time. Let's move down below on our page to solve this problem. So the first thing that we need to do is write our flow diagram, which we've done, and we've identified everything that we need. So the second thing that we should do is we should write the general balance equation and take a look at the overall system and our species. So real quick, let's do that. Let's say we have three things to balance. We can balance the overall system. We can balance benzene. And we can balance toluene. So let's write the general balance equation. Input minus output plus generation minus consumption equals accumulation. All right, so this is a mixing problem. And many times mixing in the name basically means that we're putting one stream in, doing something to it inside, and then we're getting two different streams out, one that's slightly more pure than the other. So the idea behind a distillation column in practice is that you take a stream of things that are very close in composition, or the amount in composition, right? 45% benzene, 55% toluene. It's pretty half and half right here. And the idea with the distillation column is that the overhead product pulls out one of the components predominantly. So you can see there's 95% by mole of B. So the overhead product is mostly benzene. That means we're going to expect this bottom product to be mostly toluene. We're trying to separate the two out. So mixing problems in general is a kind of equation where we're going to have no reactions occurring. So if no reactions occur, we know generation equals 0, consumption equals 0. And based on kind of the fact that it's a mixing problem and looking at what's going on in the system, there's not a whole lot that can accumulate in this distillation column at present. It's just a way to mix and separate streams. So we know that there's also going to be no accumulation occurring in the system. Okay, now let's check and make sure that that's true for everything. So in terms of the overall system, there's nothing that's accumulating overall in the distillation column. So that's good. In terms of just benzene, there's benzene in the input, there's benzene in the two outputs, but there's no benzene being generated or consumed or accumulated. And then let's check toluene. Toluene comes in, toluene comes out, but it doesn't accumulate inside here. There's no generation or consumption. So when we simplify this balance down and we say that input equals output, for this particular problem, this holds true for all three balances. So remember our integral balance, that wasn't the case with air, right? Or hexane in that balance. But in this particular problem, we just did the check to prove it for all of them for ourselves. All right. So probably the easiest balance to do at the start is maybe an overall balance, right? Like, let's try an overall balance first. So an overall balance is going to say input equals output. So what's the input here in terms of mass? Well, it would be M1 in. We don't know what that is, so we should have probably labeled it. We don't know what that is, right? So we've got M1 as an input, one input. Okay? We've got two different outputs. So we've got M1, sorry, grab my paper. We've got M1 coming out and M2 coming out. Okay. So one of the problems that we have right now is that we really don't have any of those masses. We don't have this one yet. We don't have this one yet, but we maybe could find M in. So let's just do that real quick. Because remember, we're going to have to find these other two masses. So this equation for the overall balance is probably going to help us out at some point. We just don't have these two terms right now. So if we know one of them, we can find the other if we have M in. So let's do that. So we set this up with a reminder that density equals mass flow over volumetric flow. So that means if we want to find the mass flow into the system, we take the density of the mixture and we multiply it by the volumetric flow into the system. Hopefully that makes relatively good sense to everybody. So I'm going to plug some numbers in here. We already solved for the rho of our mixture that was 872 kilograms per meter cubed. And our volumetric flow, if we go back to our diagram, is the 2,000 liters per hour. So let's plug that in. 2,000 liters per hour. Now, before you do your calculation, make sure that you have some units that make sense. We have meters cubed and liters, so we need to do a conversion because if it's a mass flow, we want kilograms per hour. So we know that 1 meter cubed is the same as 1,000 liters. So if we multiply through, we should get a mass flow rate of 1,744 kilograms per hour. So this right here represents m dot into the system. Okay, so maybe that'll help us later on. So that's the overall balance, but that didn't help us get what we need. So we're going to have to do some balances on some other species. So let's flip over the page to do that and have a nice clean page for benzene and toluene. All right, so let's first write our balance for benzene. So let's do our benzene balance. If we look at benzene and we do a mass balance, we have input equals output. Same thing that we've had, right? So we know that we're going to have X B in times M in equals XB in 1 times the mass in 1 plus XB 2 times the mass in 2. So all this is input equals output. Now we know this number right here, this one is 0.45. We just found M in. M in we found is 1,744 kilograms per hour. If we flip back to our flowchart, we actually don't know anything about mass up here yet. So we'll talk about this in a second. So there's nothing that we can plug in here. And then down here, there's not a lot we can do yet here either, right? So let's just keep that in terms of variables right now. Okay. XB2, M.2. Okay. So real quick, let's do some circling or do some underlining, whatever works for you. We're going to need this value here, this M1, and we're going to need this M2 in order to solve. So those are unknowns. There might be a way to solve for this. So maybe we can find this from YB1. We'll think about that. We might be able to find this, but that one's kind of challenging at this point. So that's something that we need to think about. And that doesn't really give us much to work with. All right, so that means that we need to write other equations. So let's write our toluene balance. So here comes the toluene balance. We're going to have xt in m dot in equals xt1 m dot 1 plus xt2, make my t's very clear, there we go, times m dot 2. All right, what can we plug in? Well, same thing here. We can say that this is 0.55 times 1,744 kilograms per hour. So we've got everything on the left side, but unfortunately, we don't know anything about the right side yet. And so that's kind of a bugger, right? We've got some problems there. So same kind of thing, right? We know that this is the same as 1 minus xb1. So maybe that could help us out. We know that this one has to be 1 minus xb2, but we still don't know m1 and m3. So we've got to come up with some other equations in order to solve this particular problem. All right, so we need another equation. So the other thing that we talked about was that 8% benzene, right? That number, so let's flip over to our diagram, right? This is 8% of the benzene in the feed. So we need to kind of think, what does that mean, right? In terms of something that we have. Well, we know that in the feed, right, the total feed of the system is the M in. So the benzene in the feed is the mass fraction of benzene in the feed times the mass in, right? That's the mass of benzene in. Okay. So if the mass in 2 of benzene is 8% of the mass of B in the input stream, then what that means is that the mass of benzene in stream 2 is that 0.8 times 0.45 times the mass into the system. So what's really critical here is that it's 8% of the benzene in the feed. It's not 8% of the total feed. So you have to remember that if you're multiplying a mass fraction by a total flow, you're effectively getting the amount in that stream. So this is the number that needs to be multiplied by the 0.8. So you've got to multiply your 0.8 by that mass fraction, the 0.45, and the mass in. So we actually know the mass in. So real quick, let's grab this number here. And so if we plug that in and we do all of our calculations, same number here, the 1,744 kilograms per hour, we can find that m.2b is equal to 62.8 kilograms of benzene per hour. And that's only kilograms of benzene, and that's important to note here. All right, so what does this mean in terms of what we have? Well, let's go back up to our benzene balance. Let's look at this term right here. If you're multiplying a mass fraction by a total mass, this term here is the same as m dot 2b. It's basically the mass flow of benzene in stream 2. These are the same things. So what we just found down here is that number. It's the component of benzene that's in that stream. So this number is equal to this whole quantity right here. So that's helpful because if we have this whole quantity right here and we knew something about this, we could find M1, right? So let's rewrite this down here. So let's go back to our benzene balance. So benzene balance, and I'll move this up in just a second, benzene balance. Let's bring down everything that we know. So we know that 0.45 times 1,744 kilograms per hour is equal to XB1. We don't know anything about that stream and its composition, but we now know that this whole term over here is that M dot 2B. And so that number right there is the 62.8 kilograms of B per hour. So now if we think about strategy moving forward, here's the next part of the video, the strategy moving forward. This we need to find using YB. How do we go there? All right, so I'm going to pause this video here because it's already gotten pretty long, and we're going to finish solving this in the next one.